Hi, in this talk, we will explore the issue of distribution shifts in building fair prediction models. My name is Harvineet, and I am a PhD student at NYU. The work is done jointly with Singh, Vishwali Mhasawade, and Chunara. Let's motivate the problem through a stylized example. Say we are a healthcare provider that has multiple hospitals across the country. We want an algorithm to decide how to allocate our limited care resources in an efficient and equitable manner. For example, we want to decide which patients to follow up more regularly. With the goals of efficiency and equity in mind, say we take data from one of our urban hospitals and develop a fair machine learning model. Now, the question that we ask is, will this model remain fair when deployed in a different setting, say a rural hospital? Perhaps the rural hospital has an older patient population or follows different clinical practices. In other words, the data distribution shifts between the two hospitals. Now, this raises some natural questions. How does this shift affect the fairness properties of our model? And further, how should we build the model in the first place to guarantee fairness when distribution shifts occur? But do distribution shifts matter? Yes, and for the following reasons. Firstly, distribution shifts occur commonly in practice when we deploy machine learning models and lead to loss in model accuracy. In healthcare, for example, using a model trained on images from one X-ray scanner to another may render the model useless. Similarly, examples of shifts can be found in a variety of domains ranging from text analysis to satellite imagery. The second reason is that in addition to loss in accuracy, distribution shifts also affect fairness guarantees of the model. Lastly, the datasets we have access to might systematically differ from the data actually observed in the world due to biases in data collection. For example, minority populations are underrepresented in facial recognition datasets, leaving us with a shifted train distribution to work with. For these reasons, it is important to build systems that account for distribution shifts. So, our goal is to build a model which remains fair and accurate as the data distribution changes. Now, there is extensive work on addressing shifts in machine learning under the name of domain adaptation, but this literature does not study fairness properties of models under shifts. Some work in algorithmic fairness do address this problem. However, they require access to data from each deployment setting while building the model. Thus, the current methods are infeasible when we expect shifts that we haven't seen in the past. Also, these works do not characterize when it is possible or impossible to build models that remain fair under shifts. Thus, our main contribution is a method that guarantees an accurate as well as fair model under shifts. We do not require deployment data to be available during model training. Thus, the method provides guarantees for unseen shifts. Further, we characterize the types of shifts that our method can handle. Now, before discussing the method, let's quickly review the standard setup of learning fair models. In this setup, the fair learning problem is reduced to that of minimizing some loss subject to some fairness constraints. The loss, for example, can be squared error between the true and the predicted outcomes, averaged over the train distribution. Important to note is that the loss depends on the model theta as well as the data distribution p. To this optimization problem, we add a fairness constraint to control the violations of a user-defined fairness criterion. One such criterion is demographic parity, which aims to control the difference in predicted outcomes across the two different sensitive groups. Note that the fairness constraint as well is a function of the model and the distribution. Now, with this quick review, we are ready to state our problem more formally. The problem on the right is what we care about, that is, solving the fair learning problem for the test distribution. However, as stated earlier, we do not have access to the test distribution beforehand. Now, one approach is to ignore the shift and learn what we can from the train distribution itself. However, the loss and the fairness constraint can change arbitrarily from the train to test because of the shift. For example, the model can learn correlations that only exist in train, thus it will incur higher loss when evaluated on test. In general, such a solution will not have any performance guarantees. So, how can we proceed? One way forward is to restrict what we can learn from the trained data. We carefully restrict the models that we consider such that the following two properties hold. For every model, the loss and the fairness constraint is the same in both the train and the test distribution. As a consequence, if we find a good solution for the train distribution, we can guarantee a good solution for the test as well, since the optimization objectives are the same in the two problems by construction. That is, the key idea is to ensure that both loss and fairness constraints are invariant under the shift. Note that by restricting the class of models, we may lose out on accuracy as we are ignoring some valuable information from the trained data. But by ensuring invariance, we can certify good performance for unseen test distribution. Now, how do we ensure such invariances? In brief, the solution proceeds in two steps. First step is to represent all plausible shifts using a causal graph. The second step is to identify the invariant information using the concept of interventions on this graph. In the rest of the talk, we will see the mechanics of these two steps through a toy example. Say we want to predict whether someone has flu or not from three features. Two of these features are those that directly affect the chances of getting flu, namely age and other risk factors like weather. The third feature is a symptom of the flu, namely measured temperature of the person. Now assume that we represent the cause-effect relations among the variables in a causal graph given on the right. For example, an arrow from Y to T means that getting flu causes the measured temperature to change. Next, we use this causal graph to represent the types of shifts we expect to occur. An additional variable S points to the variables which may differ between train and test distribution. In this case, S points to A and T. That is, we suspect that at test time, the age distribution can be different, perhaps an older population, and we suspect temperature readings to have higher measurement error. Perhaps these will be self-reported instead of being clinician tested. With this extra information, let us see the behavior of different models in a simulation setup. In this simulation, we will generate data via this process on the right, which specifies the functional relationships among the variables in our causal graph. Here, the exact equations are not relevant. Important to note is that we can vary a parameter gamma, shown in red here, to get datasets with increasing magnitude of shift. The plot on the left will show accuracy of a model on the shifted test set. The numbers on the x-axis denote the value that we used for the parameter gamma while generating the test set. As we go to the right, the test sets shift further away from the train set. Let's start with the naive approach. That is, we train a model which extracts all possible information from the trained data. Namely, we regress Y against A, R, and T using any machine learning model. In the plot, we observe that the accuracy degrades as the test set shifts. The reason is that the model relies on statistical correlations between Y, A, and T, which are not valid under shifts. For example, at train time, the measured temperature is a good predictor of flu, but as we increasingly add measurement error in T, relying on this noisy measurement of temperature results in inaccurate predictions at test time. So, how do we restrict the correlations that we learn? We leverage interventions on the graph to selectively remove these correlations. This idea has been used for domain adaptation in the past by Subhaswamy et al. We extend it to the fair learning problem. We start with the original graph and intervene on variables that the shift indicator S points to, namely A and T. This intervention, written using the do operator here, artificially fixes the distributions of both A and T. As a result, the new distribution does not vary with S since we have fixed the components that did depend on S. In other words, the interventional distribution is invariant to shifts. Invariance implies that using this distribution in downstream learning tasks does not extract any correlations which are specific to the trained distribution. Now, we must perform additional checks to ensure that this distribution is invariant with respect to the fairness criterion as well, the details of which we omit in the presentation. The last step is to use the rules of do calculus to identify the loss and the fairness constraint for this new interventional distribution, and then solve the fair learning problem. In the flu diagnosis case, the problem reduces to using only A and R as features while solving the fair learning problem. Now, with the resulting model shown in the red in this graph, we observe that the accuracy does not degrade with shift. Also, if we plot unfairness against the magnitude of shifts, we observe that the fairness violation also remains low as the distribution shifts. Thus, as predicted by theory, the proposed approach satisfies invariance in both accuracy and fairness. So to summarize, the steps involved in the approach are as follows. First, we represent prospective shifts using the causal graph, which is augmented with the shift indicator S. And then we find fair models that are invariant to S using interventions on this augmented causal graph. An important caveat is that finding such an invariant distribution through interventions is not always possible. In the paper, we list the types of shifts and fairness criterion for which our method works. This includes a class of covariate shifts, which are shifts where covariate distribution changes, but the conditional distribution of outcome given covariates does not change. The fairness criteria we can handle include well-studied statistical measures of fairness such as demographic parity and equalized odds. Further, in the paper, we showed that the resulting solution is worst-case optimal, which means that it guarantees robustness against the worst shifts. We experiment on a real-world dataset where the task is to predict whether a patient will develop acute kidney injury using their medical records from the ICU. We posit the causal graph shown on the right, which relates features such as patient's demography, their lab tests, with their AKI diagnosis. We train on the original dataset and test on different shifted versions of this dataset where we artificially add measurement error in one of the lab values. Using the graph as shown earlier, we identify the invariant distribution to such shifts. In experiments, we find that our approach, shown in red, achieves stable accuracy as well as low unfairness. We compare that with the domain adaptation method, shown in orange here, that only accounts for invariance in terms of accuracy. As expected, it does well on accuracy, but it has more fairness violations on the test sets. So, in summary, these results underscore the importance of considering invariance in both fairness and accuracy while accounting for shifts. To conclude, we find that changes in data distributions affect both accuracy and fairness, and leveraging causal understanding of the domain, we show how to mitigate these effects for a class of covariate shifts. Thank you for listening. Please reach out for any questions or feedback. I look forward to the discussions.